I like to call this video EKG, like an electrocardiogram for your heart, but it really is about electrocell potential, the equilibrium constant, and Gibbs free energy. Related though, because it's about electricity in both cases, you should already be able to identify and balance redox reactions, assign oxidation numbers for elements and compounds, and calculate a voltage, and define Gibbs free energy and equilibrium constants. But by the end of this video, you'll also be calculating the Gibbs free energy of a cell using delta G equals NFE, calculate the equilibrium constant of that cell, and predict if a cell is spontaneous or favorable using those voltages, Gibbs, or equilibrium constant. And last, identify concentration cells and explain why the voltage might not be exactly what's on the reference table using that Nernst equation. So the question of this video is, recall that the voltage of AA batteries was 1.43 volts in our last video. How is it related to Gibbs free energy and the equilibrium constant if this is the reaction that was overall going on in the battery? So we'll come back to that. We have to talk about these things. So delta G for a redox reaction can be found using the formula delta G equals negative NFE, where N is the number of moles of electrons transferred. F is a constant, is Faraday's constant, where it's equal to 96,485 coulombs per mole, also known as 96,485 joules per voltage mole. So it's just telling you how you can convert between the number of electrons that are going through your battery to something called coulombs, which is part of your current, right? So the electromotive force or voltage can be related to the equilibrium constant using both equations. So once you know your Gibbs free energy from negative NFE, you can calculate your Gibbs, your K from delta G equals negative RTL and K from the last videos, the last unit. And what we should know so far is that in this reaction is an example of ammonia being formed. And it's spontaneous if it's something spontaneous just means that it's favorable. And it's favorable as long as your K is bigger, right, than 1. So where you have more ammonia than you have nitrogen and hydrogen. Another example is that your Gibbs is negative. And now what we're seeing is we want our voltage to be positive. They have to go together. It would be not spontaneous if the reaction is reactant heavy, so you have more nitrogen and hydrogen, your K is less than 1. If your Gibbs is positive, and now we know if the voltage is negative. So we're going to do some calculations and assume they're all at 25 degrees so that we can use the degree symbol. The Gibbs is negative NFE, so the number of electrons is found by looking at one particular particle, like gold in this example. Gold is going from 0 to +3, so that's 3 electrons lost, but it happens twice, so 6 electrons lost. Or you could look at calcium and say calcium went from +2 to 0, which means it gained 2 electrons, and it happened 3 times. So either way you look at it, there were 6 electrons transferred. You're going to put your Faraday's constant in. I rounded it up because 3 sig figs is usually pretty normal, so I rounded mine to 96,500, and you can do the same if you'd like. And then I use my electron cell potential chart that I gave you in class to figure out what the voltage would be. And what we're seeing is that calcium is the one that's reducing, so I copied calcium's reduction, and I subtracted gold's reduction, right? I subtracted it out because it's actually oxidizing. And when you multiply these numbers, you get 2,530,000 joules, which is a lot of joules. But notice two things. It's in joules because this 96,500 is in joules, not kilojoules. So it's actually 2,530 kilojoules, right? Still a lot, and it's positive. What that means is this is not a spontaneous reaction in any way. It's not favorable because you require that much energy. You also knew that probably because the voltage was negative. Let's do it again. Maybe you want to pause the video and see if you can get it right. In this example, we're seeing that 2 aluminums are gaining 3 electrons each. So again, is 6 electrons being transferred? Or you could look at magnesium. The Faraday's constant is a constant, and you're copying from the reference table. And in this example, we're seeing that magnesium is oxidizing and aluminum's reducing. So aluminum's going to be written first as a reduction from the table. And magnesium says negative 2.37, but we're reversing it. So we're negating that, or cathode minus anode. And when we multiply these numbers together, I got 411,000 joules released. That means it's a favorable reaction. And we also knew that because the electron potential was positive. So another example is they can ask for the K of this reaction, and it looks like you don't have a lot of information. But remember, you always had the potential chart, so you can start there. The Gibbs is 2 electrons being transferred. You can tell by the charges, 96,500, and then the cathode, which is the reduction of copper, minus the anode, which is the oxidation, notice the minus, of tin. And then when you multiply the numbers out, I get negative 92,640 joules. I probably should have sig figged that, but I didn't. But what we do see so far is it's not only favorable because the voltage is positive, but anytime the voltage is positive, the Gibbs is negative, favorable, releasing energy. So I'm expecting the K to be pretty big and favorable. I'm going to calculate it. So I'm going to put that Gibbs in. I'm going to say negative R. R is 8.314 from the reference table in joules. T, temperature, 298 because it's 25 degrees Celsius. And I'm going to solve for ln of K. So I divide out by 8.314 and divide out by 298. To get ln by itself, you raise that to the exponential e to the, and then the K comes out to be 1.73 times 10 to the 16th, a large positive number, a number larger than 1 that I expected. Maybe try this one, and we'll see if you got it right. So for this one, the Gibbs is, again, 2 electrons being transferred at 96,500 coulombs. And this time, the reduction is for iron at negative 0.44, and we're subtracting the silver because it's oxidizing at 0.8. That gave me 239,000 joules, which is positive and unfavorable, but we probably knew that because of negative voltage. And then to confirm it with the K, we're going to put that in for the Gibbs, negative 8.314, your temperature at 25 degrees, and then solve for K. My K came out to be 1.12 times 10 to the minus 42, and that shows that it's really small, reactant heavy. So in summary, and you should really write this down, is if you see a negative G, it's spontaneous or favorable, which means it's a positive voltage and a K that's less than one product, more than one product favored. If it's not spontaneous or not favorable, the Gibbs is positive, the voltage is negative, and the K is small, less than 1, reactant favored. Really, really important chart. You can't have any crossover. This Nernst equation is not on your reference table. It would have to be given to you in the question, and it's for non-standard reactions. So this is the guy Nernst who figured it out. He's noticed that in certain conditions that are not 25 degrees or not perfect scenarios, where you have 1 molar solutions, if you have anything other than 1 molar solutions, he figured out how to get the new voltage. So again, that voltage is only true at 25 degrees Celsius and 1 molar. But your solutions in your body that produce, electricity and have synapses between the brain and your parts and all that stuff, they were nowhere near 1 molar solutions, right? So there has to be a way of calculating the voltages when they're not 1 molar solutions. And this is the crazy equation, but it's actually not that bad because we already know what R is, 8.314. Temperature is whatever temperature is in the question. N is how many electrons are moving, and Faraday's constant is 96,500. The only difference is you're using that correction times the natural log of Q. Q is the products of a reactants, just like K, but they might not be 1 molar, so they won't cancel out as ones. And then E with the degree symbol is a normal voltage you can find in your reference table, fixed for this E without a zero. The E without a zero is for any temperature or any molarity that you plugged in. So using that equation, here's an example. Predict if cobalt plus iron ions will replace and make cobalt ions and iron solid, and it's spontaneous at these molarities and this temperature. So we're going to plug our numbers in. The E regularly on your reference table shows that we're trying to see that iron reduces at negative 0.4 copied, and then we were going to negate the iron, which was negative 0.28, so we're summing those together. We can already see that this particular reaction is usually not, in 1 molar solutions, is usually not favorable because I'm getting a negative voltage, but we're going to see if these molarities help at all. So when we minus the R, 8.314, temperature 298, the N, number of electrons, are 2, and the Faraday's constant, 96,500, we're going to multiply that by the natural log of Q. Q is the products over reactants. Remember, we don't put solids in, so it's just cobalt ions, 0.15, over iron ions, 0.68. Products over reactants. No big news there. When we put this whole thing in our calculator, I recommend doing the right side first and then subtracting. I got negative 0.16 volts, and that means no, it's still not spontaneous even at these molarities, because a negative voltage is not good, right? We want volts to come out, but not negative. And at number 2, we have another example of cadmium replacing iron, and we want to know if these molarities and this new temperature of 30 degrees Celsius will make it spontaneous. So again, I'm using the equation. I'm looking up iron reducing and copying it down just like before, negative 0.44, but I'm subtracting the cadmium because it's oxidizing at negative 0.4, and so that gives us Again, still a negative voltage. It's a negative 0.04 voltage, and it's showing that that reaction normally is not favorable. So let's see if it is favorable at this new temperature and concentrations. I put in my 8.314 for R, T 298, 2 electrons transferred in 96,500. A natural log of products over reactants. The products are cadmium at 0.1. The reactants are iron at 0.6. Remember, the plain elements are not written. It's only the charged particles, because plain elements don't affect the equilibrium. Solids. And when we calculate this out, I got negative 0.017. It's getting a little bit better, but it's still not good because we don't want a negative voltage. So just again, one more time, the EKG correlation, some people like this picture in their books. E of the cell can be changed to Gibbs using the NFE formula. Gibbs can be changed to K using the RTLNK formula. And E to K can be calculated using the Gibbs formula, the new Nernst equation. But I prefer not using this because you can actually go backwards, right? We can go through Gibbs to get to cell and avoid this whole mess of RTNF. There's one last thing that we have to talk about. It's concentration cells, particularly important in your own bodies, like I said before. You can actually have the same substance at both electrodes as long as the concentrations are different. So what you're seeing here is the nickel anode has a low concentration, it's dilute, and the cathode is concentrated. And over time, electrons are transferring through the voltmeter until they become the same concentration. So that way, some of the nickel in those anodes and cathodes are changing. Oxidation always takes place at the anode. In this case, it's going to be more dilute solution, so that way we can get that anode to dissolve and increase the molarity to 0.5. That means the cathode has to gain electrons, reduction at the cathode, and that way that cathode will take some of the nickel out of the solution and deposit it onto the cathode. Remember, fat, red, cat. So we're noticing, and if you want to write this down, that the anode is always the dilute solution and the cathode is always the concentrated solution. And here's just an example of what's going on in your body. You actually have cell membranes where you have different types of salts on either side of your cell. And sometimes some of the salts will go through the membrane and try to make it so the concentrations are the same, even though they're both soluble salts, right? So here's an example of how zinc works in your body. If you went from a 0.1 to 1 molar solution of zinc solution, we want to know what the voltage is. So we're going to do, normally it would be 0 if they were all 1 molar, but the R is 8.314, the temperature is 298 because we said 25 degrees. The natural log of products over reactants is 0.1 over 1 because we're going from the dilute to the concentrated. And the number of electrons that are transferred is 2 per 96,500 coulombs. And if we calculate it, we get a very, very small voltage, but there is a voltage, right? It's putting out 0.0296 volts. Nothing that will hurt you and shock you, but enough to make your limbs move, right? You need to have these type of stuff in your body. So back to the question in the video, recall the voltage of AA batteries is 1.43 volts. How is it related to Gibbs and equilibrium constants? Well, we can put it into our calculation. We remember from the previous video, we knew 2 electrons were moved from the zinc 0 to the zinc plus 2. Always 96,500, and the voltage was 1.43 volts as stated in the question. This gave us a negative 2,760,000 joules per mole. Definitely spontaneous for Gibbs, right? A very favorable energy to release. And if we do it for K, we're putting in the Gibbs value equals negative 8.314, 298 because it's the temperature, ln of K. We'll divide and then raise it to the exponential of power. So the natural log is 11.14. So if you put E in your calculator than 11.14, you get 6.89 times 10 to the 4th. A very big K means it's very product heavy and very favorable. At this point, you should be able to use the Gibbs and the K equations.